Hi guys, and welcome to this video on greatest common factoring. Greatest common factoring is the method of taking the largest number that is a factor of multiple terms in a polynomial and removing it and rewriting it as the product of the greatest common factor and its leftovers in order to factor and solve expressions that we might not necessarily be able to solve with a Xbox method of factoring. So let's get started. So you are learning to remove the greatest factor from an expression in order to factor it. It allows us to factor cubics and quadratics that don't have constants. And you can factor an expression like 4a squared b squared plus 8ab squared, a complex multivariable polynomial, if you're successful at learning this. So the greatest common factor of two numbers is the greatest integer that is a factor of both numbers. For example, the GCF of 12 and 18 is 6 because it's the largest number that goes into both of them. The process is similar when you're asked to find greatest common factor of two or more monomials. So example, if I have 4x and 10x to the third, the factors of 4x are 1 and 4 as a pair, and then 2 and 2 are a pair. So that's important. I want to list out factor pairs, and then x is only a factor of itself. For 10, 1 and 10, and then 2 and 5. And then for x to the third, x times x times x. So the largest factor they have in common is 2 numerically, and each one of them has an x, at least an x, okay? This one has 1x and this one has 3 x's, but because this one only has 1, the greatest common factor is a single x, not 3 x's, but a single x. So that means we have 2x is the GCF of these two expressions right here. The GCF of these two is 2x. So applying that to factoring, what you want to do is to factor the GCF out of a polynomial, you do the following. First, you find the GCF of each polynomial, or of each term in the polynomial. Second, you express each term as a product of the GCF and another factor, so you would have something like this, where it'd be the GCF times the leftovers plus the GCF times leftovers. And then you undistribute. You like reverse distribute to factor out the GCF, and this is what you should end with. So let's take a look at that in an example. I have 2x squared minus 6x. So if I want to factor this out, the first thing I'm going to do is factor the GCF here. Try to find the GCF of 2 and 6. So 1 times 6 and 2 times 3. And for variables, to write out variables, I just list out. So it's x squared breaks down into x times x, and this one breaks down into x. So what then I am going to do is realize that I've got a 2 and a 2 here, and each one of the each term in the polynomial has an x as well. So the GCF of this expression is 2x. And I can rewrite them as the product of 2x times x for the first term, and the second term can be written as 2x times, and then what's left over here is 3. So then I can reverse distribute, so I can yank these out, and I get 2x times x minus 3 as my factored version. And if I check it and redistribute, so if I would take this here, and I'm going to just duplicate it real quick, and I'm going to reverse distribute, or I'm going to actually distribute, that would turn into 6, not 6, it would turn into 2x squared minus 6x, which is what we started with. So our factoring is correct. So here I have a complex multivariable polynomial where I have multiple variables happening at the same time. So in order to remove the GCF, I'm going to have to find the greatest common factor of the numbers and how many of each variable each term has. So 12 can be broken down into 1 times 12, 2 times 6, 3 times 4, and 6 can be broken down into 1 times 6 and 2 times 3. A squared would be written as A times A, and B squared would be B times B. And then the same for the 6A squared. A squared is A times A, and B over here. So then the greatest common factor that I can see is a 6. So numerically is a 6. They both have A squared in them, and they both have a B. So the largest factor, the GCF, is 6A squared B. And so if I write that, and I can write that GCF as a product of the, or I can rewrite the expression as a product of the GCF times what's left here is a 2 and a B, plus what's left over here is a 1, and that is multiplied by the GCF. So when I reverse distribute these, so this is coming out and this is coming out, when I reverse distribute them, I get 6A squared. Ooh, my screen lagged a little bit. 6A squared B times, now what's left here is a 2B, and what's left over here is a plus 1. So if I were to go back and check and redistribute, 6A squared times 6A squared B times 2B would in fact give me 12A squared B squared. And then over here, taking everything out leaves you with a 1 if you factor everything out of it, because factoring is division. So here, again, is another multivariable polynomial. So what we're going to just do is start factoring the coefficients first. So 1 and 8, 2 and 4. A squared would be A times A, a B, and C times C. Over here, 1 times 6, 2 times 3, a single B, and then C times C. So if I look through my factors, there's a B in common, 2 C's, and a 2. So the GCF for these two terms is a 2BC squared. So I'm going to factor that out, and when I do, I am left with a 4. So I'm skipping the step. I'm going to skip the step here of pulling out, rewriting, and then pulling out. I'm just going right to the part where I've already pulled it out, like I've already undistributed. What's left here is a 4 and a squared. And over here, a 3 is all that remains. If I go back and I distribute this, I would get 2 times 4 is 8, A squared, B, C squared. And over here, 2 times 3, negative 3 would be negative 6, B, C squared. So yep, we factored it correctly. So what's the point of removing a greatest common factor? If we remove a greatest common factor, we can sometimes then factor the resulting expression if it's a quadratic using the trinomial factoring method, using our Xbox method. 5x squared plus 25x plus 30 would be a difficult quadratic polynomial to factor, but if we factor out a 5 first, it becomes much easier to do so. If we're factoring a quadratic, we can use the zero product property, or if it's a cubic or any sort of polynomial equal to 0, we can then use the zero product property to find the x-intercepts of the equation. So let me give you an example. Find the x-intercepts of this quadratic equation. I would immediately try to go in and be like, I'm going to do an xbox. The problem is it doesn't have a constant. Because this doesn't have a constant, I am going to instead I'm going to have to try to do GCF factoring. So I'm going to realize that 5 would be 1 times 5, and that's the only factor since 5 is prime. And then x times x. For 10, it would be 1 times 10, 2 times 5, and we have an x over here. So they each have one x in common, and they each have a 5 in common. So we're going to rewrite it as the greatest common factor, 5x, times the leftovers here, 1x. So I'd write that like that, and 2x, since I have to use this pair, 2x. Or no, the x is used, so it would be x plus just the 2 equals 0. It's at this stage now that I could use the zero product property to break this apart into two equations. 5x equals 0, or x plus 2 equals 0. Because remember, the zero product property says that a times b here equals 0. Then a equals 0 or b equals 0. A is this expression, b is this expression. So then dividing by 5 over here, I get x equals 0, or subtracting 2, x equals negative 2. So that tells me that the two x-intercepts of this equation are negative 2, 0, based on this answer, and the other one is 0, 0, and that's based on this equation here. So despite the fact that this didn't have a constant, I was still able to factor it in order to find its two zeros. This quadratic has a coefficient in front of the first variable. We don't currently have a method for factoring when we have a coefficient in front of the x squared. However, if we were to perhaps reduce it and remove the coefficient by factoring first, we could then factor the resulting quadratic trinomial. So what I am going to do is look for factors of the numbers. So 1 times 2, 1 times 8, 2 times 4, and then 1 times 24, 2 times 12, 3 times 8, 4 times 6. And if you're asking yourself, well, why didn't you look for any factors of x? Well, this is x to the second, x to the first, and then there are no x's here. So I don't even have to bother because I know without an x here, x cannot be a greatest common factor of all 1, 2, 3 terms. So the greatest common factor that I'm seeing is 2. So let's write it out. 2 gets multiplied by x squared minus, so what's left is a 4x, and then what would be left here is the 12, and that's equal to 0. Now I can factor this resulting expression here using my Xbox method. So negative 12 and negative 4 go in my factoring box. So negative 12 means that I'm going to have a positive and a negative. And the factors of 12 are 1 and 12, 2 and 6, and 3 and 4. So I'm looking for two numbers that differ by 4 when they are subtracted, since one of them is negative. But it's got to be negative 4, so it's got to be the bigger number first, or the bigger number needs to be negative. So 2 and 6 are the choice that I am going to make. So that allows me to write the expression as 2 times, and then an x plus 2 times x minus 6 equals 0. And then I can use the zero product property. So I'm going to use the zero product property now. So use the ZPP. Because the coefficient is a number and only a number, I ignore it when I write my zero product property statements. So I'm just going to make the statement x plus 2 equals 0, or x minus 6 equals 0. So when I solve for x, I get x equals negative 2, or x equals 6. So that means the two x-intercepts that we just found are, so the two x-intercepts are negative 2, 0, and that's based off of this answer here. And the second one would be 6, 0, and that's based off of this right here. And so finally, The last example is that we can use GCF factoring to factor cubics too. If we remove a variable, this becomes a quadratic, which we're pros at factoring. So let's do that. Find the x-intercepts of the cubic equation. I'm going to look and I see no number in front of the coefficient here. So there's nothing that I can factor out numerically because this is only a 1. And I don't bother factoring 1 because it doesn't change the value. So I am going to write out all of the x's that they have in common, which is 1. They have 1x per term. So I'm going to factor that x out. X times x to the second power plus 10x plus 25 equals 0. Okay, I can factor this using the tried and true method of Xbox. So 25 on the top, 10 on the bottom. I know for a fact that the two factors of 25 that add to 10 are 5 and 5. So then I get x times, so then x plus 5 and x plus 5 again equals 0. Here now, because I have nothing but x statements, x plus, I can use the zero product property. Because this is a variable coefficient, I'm going to include it in my zero product property statements. So the first one is that x equals 0. That's one of the things. Or, and then I can say x plus 5 equals 0. Or, finally, this x plus 5 equals 0. X equals 0 is already solved. So subtract 5 from both sides. You know how it turns out. X equals negative 5 or x equals negative 5 again. So my three answers lead me to the x-intercepts of this cubic equation, and they are 0, 0 based on the first one, negative 5, 0, and then negative 5, 0 has some duplicity here, so it is the third 0 as well. So in summary, guys, factoring by removing the GCF is the reverse of the distributive property for polynomials. And our quadratic functions are definitely polynomials. We can do GCF factoring over multivariable polynomials as well, such as 4a squared b squared plus 2b squared c. They would each have a 2b squared in common. And is incredibly useful for finding quadratic x-intercepts when you don't have a constant term, and it helps us get a beginning handle on finding cubic x-intercepts. So thanks for watching, guys. I'll see you in the next video.